Hi everyone. So this is an algorithm that I just found out about like 2 days ago, and I was really surprised to see that there wasn't much talking about it, and there was not much that I could find on it besides really this one article. I really couldn't find many code implementations or really anybody talking about it, but this is something that's really interesting to me as someone that works with computational musicology. So this is the Krumhansl-Schmuckler key finding algorithm. So the idea is, if I give you a piece of music, can you tell me what key it's in and whether that key is major or minor? Now, doing that as a trained musician is pretty easy after a while. If you have a relative pitch, you can kind of get, the exact note. Or if you have perfect pitch, you can sometimes get the exact note and also tell whether or not it's major or minor based on, how much ear training you've had and things like that. Doing that as a person is pretty easy. I've never considered the fact that you might have to do that in a program at some point because I've never really had to use that. Um, and if I did, I would probably just use AI to do it. But the fact that we have an algorithm specifically for that is really interesting to me. So the way that this works is actually using quite a bit of statistics. So some things that are kind of pre-calculated out from the authors of this algorithm. They give us these kind of coefficients of whether or not something is major in a certain key or another. Like for example, we could say do right here would be C, and I believe that's what they're trying to represent is do is C, do sharp is C sharp, re is D, all the way up to T would be B, because that's what they've got in this pair of this article here. So that's what we'll go along with to implement the algorithm. So the way that this actually works is by treating the pitch class profiles of the piece of music that we give it, which is basically just how many notes fit into each distribution of notes. So how many C's are there? Not just C1, C2, C3. Just tell me how many C's are there, how many C sharps are there, how many D's are there. That kind of gives me a rough idea of my pitch class profiles for a piece. Just tell me the distribution of notes across the whole piece. So we use that, and we can calculate the correlation coefficient, or the Pearson correlation coefficient, if you want to be specific, using this formula. So we treat the notes kind of as a set of coordinates, x and y. Up top here, we have it looks like basically just a dot product that gives us all the x values minus the mean x value, and then the y values minus the mean of the y values, which is the start of a z-score function. So then down at the bottom here, if this is the start of our z-score, which is just the dot product of all x minus x mean, y minus y mean, then down here is our standard deviation for those two data sets. So we can actually use that. We can kind of pair our notes up as a matrix to get a really, really good representation of what this data looks like. So I guess these values are all pre-computed out from a textbook from Krumhansl's Cognitive Foundations of Musical Pitch. Copies of this book are a little bit on the pricier side, kind of surprisingly, because it's a bit of an older book, but it might be worth checking out. But for the most part, this is a very simple algorithm, and in Python, it's really, really easy to set up. So let's take a look at that, and we'll implement it from scratch really quickly, and I'll show you a couple examples of it working. So first of all, I'm going to get this pulled up on the side, because I'm going to need these coefficients. I'm going to make a new file, not a text file, but I'll just save this, and I'll call it, let's call it key estimation.py. So there's a couple different libraries that I'll need. You might need to do pip install whatever the name of the library is if you don't have some of these. So I'm going to import Librosa. Librosa lets me read in audio files really easily and get their pitch class distribution. We'll import NumPy as NP, so I can use NumPy arrays alongside scipy.linalg for linear algebra. We'll do from typing import list, so we can give our function better documentation. And from scipy.stats, import z-score. And from data classes, import data class. So data classes are really cool. Not only can I use it to make just kind of like a C-struct style thing, but one of the things that is really cool with data classes is we can basically use it to make a function that has a constructor, which is kind of bizarre, but it's really useful in a case like this. So to make a new data class, we put the @data class annotation, and we'll call it class key estimator. So again, this will be pretty simple. I'll just write up a little documentation so you can have it with your code. So estimate the key from a pitch class distribution. Most computational musicology algorithms use the pitch class distribution in some way or another. And we've got parameters. So our first parameter will have x, which is a ND array with shape 12. And this will be our pitch class energy distribution. Does not need to be normalized. And I'll put the hyphen up here as well, just for consistency. So we don't have to do anything fancy to work with that. And then this returns. We'll have our major coefficients, so another ND array of shape 12, because we have 12 possible notes. And same thing for minor. Oops, this is equals. And as well, for each key, where C, C major, ... B major, I'll just abbreviate this, and C minor all the way to B minor. I'll put a comma here too. So for each key, from C major to B major and C minor to B minor, the correlation score for X against that key. So this is what we're returning. And then, just if you want, I'll put a little note here. The coefficients from Krumhansl and Schmuckler. And there's the link to that. And I'll shrink this down just a little bit so I have more room for my code. So that's our basic setup. Now I need to copy over all of these coefficients that we see on the right side. So we'll have major equals np dot as array. And we gotta copy all of this stuff in basically. So 6.35, 2.23, 3.48, 2.33, 4.38, 4.09, 2.52, 5.19, 2.39, 3.66, 2.29, 2.88. And we do the same thing for minor. As array. 6.33, 2.68. You can read their little book, I guess, if you want to figure out how they got the magic numbers. 2.60, 2.53, 2.54, 4.75, 3.98, 2.69, 3.34, and 3.17. And then this is just a little example piece that they give down at the bottom. So now, what we can do is data classes have sort of a pseudo constructor. We don't use init with a data class. Instead, we can use a thing called _post_init_. And this is basically a post constructor function. So once the object is made, this code gets ran automatically. So here's where we'll do sort of our bulk calculation, so we can actually figure out the scores for each of these different coefficients. So bear with me here. We'll do self.major equals z-score self.major. And then let's normalize that data. So major norm equals scipy.linalg.norm takes in self.major. And then we can turn it into what's called a circulant matrix, which is where each of the rows is just an offset of the first one, until basically each opposite corner is the exact same. So the top left corner and the bottom right corner will be the same value. Bottom left corner and the top right corner will be the same value. It's an abstract algebra structure that we use in linear algebra that does some pretty cool stuff like this. So major equals scipy.linalg.circulant self.major. And that's that. So we just have to copy that for minor as well. So self.minor, z-score of self.minor, minor norm equals scipy.linalg.norm, self.minor, and self.minor equals scipy.linalg.circulant, self.minor again. So that's that little bit. So we've got our circulant matrix, we've got our normalized z-scores, and we'll use both of those. Now we can make our call function. So this is what lets me treat a data class as a function, is we'll make a def call parentheses self, and takes in x, which is a numpy array, and returns, so arrows returns, a list np array. So just like everything else up above, we need our z-score again. Whoops, z-score of x. So just take every value minus the mean, and then also divided by the standard deviation if you want to be specific. And we'll calculate the norm as well. scipy.linalg.norm of x. After that, we just have 2 lines of code, and that's it. So we just have to calculate the coefficients for major and the coefficients for minor. So coefs major equals self.major.transpose, because we're doing multiplication, using dot product of x divided by self.major norm divided by x norm. And same thing for minor, coefs minor equals self.minor.transposed dot x divided by self.minor norm divided by x norm. And then just return them as a tuple. So coefs major, comma, coefs minor. And that's it. So this is my entire key estimator class. Nothing too crazy. But this is the entire algorithm right here. Everything else that we do from here on out is just fluff, so we can actually, read in and test some data files. So now, let's back up a couple tab spaces so we can get into main. And let's outline our sequence of events. So we'll read open. I'll just use MIDI file, so the MIDI file and extract the pitch class distribution. Then estimate the key of the piece using the Krumhansl-Schmuckler key estimation algorithm. So that is our sequence of events. So first of all, we have to use Librosa to actually read in our data file. So load the audio as a waveform called Y, which is just kind of standard notation for working with Librosa. And then we also store the sampling rate as SR. So we'll just prompt the user to enter the file path. File equals input, enter path to audio file, and then YSR equals librosa.load file. So very easy to load files using Librosa. Now is where we kind of get into the more music heavy side of things, or computational music heavy side of things. We have to compute the chromogram, which tells us the energy for each pitch class at each audio frame. So compute the chromogram, i.e. the energy in each pitch class at each frame of the audio. And it's not very hard to do because Librosa does it for us. Chromogram equals librosa.feature.chroma STFT, or short time Fourier transform, y equals y, SR equals SR. Librosa is very nice. Now, let's take the sum of all of this energy. So sum energy across all frames. This gives us the energy in each pitch class over the entire song. So pitch class distribution is exactly what we need for this algorithm, which is just chromogram.sum over axis 1. And then we just estimate the key using K and S, which all we have to do is just call our new data class that we made. So key estimator equals key estimator. Oops. Nothing goes in the constructor. So once this line of code is called, then post init is also called. And then major comma minor equals key estimator, and pass in the pitch class distribution, which is our X. Now, because this is going to give me all of the pitches through their index in our little coefficient array that we made, we need to create a little mapping so we can know what actual notes that we're looking at, just for human readability. So let's do that. So mapping equals 0 is C, 1 is C sharp or D flat, 2 is D, 3 is D sharp or E flat, 4 is E, 5 is F, 6 is F sharp / G flat, 7 is A, hold on a second here. Oops, nope, I skipped over one. There we go. 7 is G. 8 is G sharp / A flat. 9 is A. This is a pretty long line of code. 10 is A sharp / B flat. And 11 is B. So now I'm going to shrink this window down quite a bit so you can see the whole thing. So this is what my indices correspond to. So right up here, 6.35 corresponds to C, C sharp, or D flat, and then D, D sharp slash E flat, E, F, F sharp slash G flat, G, G sharp, A flat, A sharp, B flat, B. So we follow that exact same mapping, so it just makes it easier for us to kind of interpret the results. And now let's actually print it out. So let's print out, I'll put a little line break just to make it look nice, major key coefficients. So for I, comma, coef in enumerate major, we'll print out, using an F string, mapping sub I. So tell me what key that we're looking at, and then tell me its coefficient. Tab space, coef, rounded to 2 decimal places. And we'll basically just do this exact same thing with minor as well. So we can just copy and paste this. Change this to minor, and change that to minor, and everything else is the exact same, so we don't have to change anything. And then print out the estimated key. So print estimated key. Let's make this an F string as well. We'll do mapping sub to actually figure out which index of our coefficient array has the largest value. We'll use np.argmax. So tell me the index of the largest value in major for major key, or mapping sub np.argmax, whoops, of minor for the minor key. So tell me which of my 2 keys it's more likely to be. And then we have to do the exact same thing for figuring out just what key specifically is it. So print most likely mapping np.argmax. We could have made a variable for this as well. Major plus major with a space. If np.max of major is greater than np.max of minor, so if it's more likely to be a major key than a minor key, we'll print out whatever its most likely major key is. Else mapping of np.argmax minor plus minor. I'm going to move that off the screen. And then we'll leave a little blank line, and then just have to do our startup, which is if _name equals _main, then call main. And that should do us. So we've got everything to actually calculate the KNS algorithm, which is up here. And then everything down here is just performing our data transformation, grab all of the pitch class distribution, map it out, run it through the algorithm, and then print out the results. So if I run this, whoops, I gotta not select on the junk. Let's try this once more. So it's telling me to enter path to audio file. I've got a couple on my desktop. That's junk. Let's grab Minuet in G major by Bach. This is the famous cello piece. So copy as path, right click to paste it, delete the little quotes, and it takes a second. Don't worry about the warning. So it prints out, here's all of my major key coefficients. So out of all of these, again, G major, very likely. Out of all of these minor key coefficients, B minor, fairly likely, But again, if we compare these two, 0.86 versus 0.68, very likely to be G major, which in fact it is. And, we could also put a little line break here, just for the sake of consistency, in our printout. So if I pull this up, so that was my very last note there, whoops. So that's my tonic note. So very clearly in G major. Let's learn it again, this time with Fauré's Elegy for cello, with optional piano accompaniment. Let's run this guy. Shoot, I just did a single line run again. I'll delete that later. Right-click, paste. And depending on the length of the song, obviously this will take longer to read based on how many notes there are, because we're doing a lot of very computational heavy math. Anything involving matrices or dot products or z-scored or anything statistical, you can kind of guarantee to be a little bit on the slower side. And this piece is in fact in C minor. So if I pull this up again, listen to that note. Those are the two notes that are going on at the same time. So that is C minor for sure. And lastly, we'll do Barber's Adagio for strings. Run it once more. And this piece is in B flat minor. So let's see what this gives us. And once this is done, we can also double check just to make sure that it's the right key. Sure enough, again, there's not really a way to differentiate between whether or not something is A sharp or B flat. Just trust your instincts and your musicality. A sharp and B flat minor are enharmonic, so they sound the exact same. But this piece is for sure in B flat minor, if you check the key signature. So if I was training an AI model on something that needed to use the key signature of a piece and I didn't want to have to manually figure it out, this algorithm is very, very accurate. Out of all of the pieces that I tested this with in my own testing, I literally only found one that was not correct for the entire piece, but it could have been for just that specific movement, because one piece of music doesn't always stay in the exact same key. Sometimes we, modulate, or sometimes we tonicize a key for a certain number of measures, for example. But if we listen to this, that's our starting note. Sure enough, that is B flat, or A sharp. So honestly, this algorithm is really, really cool, and I was really surprised that there's not much talking about it, because this is extremely useful for anybody that does this sort of work. This is a really cool algorithm. So once I found this and I didn't see any YouTube videos talking about it or anything like that, I figured I would make one and just kind of go over it and show a little implementation, because it's not very difficult to implement if you're familiar with these concepts. So hopefully you enjoyed, and that is the Krumhansl-Schmuckler key estimation algorithm.